So far, we have justified the various equivalence laws intuitively, but of course there is a rigorous way to prove them using the semantics of the LTL formulas. Next, let us do such a rigorous proof for one of these laws. Say eventually phi is equivalent to not always not phi. Invariably, when doing such a proof, we fix a labeling function L and an infinite sequence of states pi, as in the definition of formula equivalence. What we need to prove are two things. That pi satisfies eventually phi implies pi satisfies not always not phi, and conversely, that pi satisfies not always not phi implies pi satisfies eventually phi. So let us prove the first of these. To this end, we assume pi satisfies eventually phi and aim to prove that pi satisfies not always not phi. From the assumption, by the semantics of eventually, we find an I such that pi I satisfies phi. Remember that pi I denotes the ith prefix of pi. By logic, this means that it is not the case that for all I, pi I does not satisfy phi. Next, using the semantics of not, we turn does not satisfy phi into satisfies not phi, because the two mean the same thing. Furthermore, applying the semantics of always, from the above we obtain that it is not the case that pi satisfies always not phi. Right? All we need in the last reasoning step is to note that these two mean the same. For all I, pi I satisfies not phi, and pi satisfies always not phi. This is by the semantics of always. We have thus obtained that pi does not satisfy always not phi. Applying again the semantics of not, we obtain that pi satisfies not always not phi, as desired. So we are done with proving this implication. For the converse implication, let us assume that pi satisfies not always not phi. By the semantics of not, this means that pi does not satisfy always not phi. In other words, it is not the case that pi satisfies always not phi. Now, applying the semantics of always, we obtain that it is not the case that pi I satisfies not phi for all I. It's just turning this into this, applying the semantics of always. Using again the semantics of not, we replace pi I satisfies not phi with pi I does not satisfy phi. This means that there exists an I such that pi I satisfies phi. Again, we use pure logic here. Something not being true for all I means that that something is true for some I. Now, by the semantics of eventually, we obtain that pi satisfies eventually phi, as desired. This completes the proof of the converse implication, hence the proof of the two formulas, eventually phi and not always not phi, are equivalent. As a side note, our proofs of the two implications are essentially mirroring each other. We could have proved the equivalence directly as an if and only if statement using a chain of equivalence statements. Okay, this example should offer you guidance on how to rigorously prove the equivalence of various LTL formulas. As homework exercise, please pick any three laws from the previous slides and prove them rigorously, as we did above. This concludes the introduction to LTL, and here is a summary of what we discussed in this introduction. We looked at the LTL syntax, how to build formulas from atoms, propositional connectives and temporal connectives. We saw some examples of what can be specified with LTL formulas. We defined the semantics of LTL formulas, first as a satisfaction relation between infinite sequences and formulas, and this was later extended to a satisfaction relation between labeled transition systems and formulas. Finally, we looked at formula equivalence and some of its laws. If you want to read more about these concepts, I recommend sections 511 to 514 in the Bayer and Catton monograph, and section 3.2 in the Huth and Ryan monograph. Note that the Huth and Ryan monograph uses different notations for the temporal connectives, which are good to know since you are likely to find them elsewhere in the literature. It uses X instead of circle for next, F instead of diamond for eventually, think of this as in the future, and G instead of box for always, think of it as globally.